Okay, so we're going to talk about the ANOVA test, which is 13.1. 13.1. Now, the interesting thing about the ANOVA test, actually, maybe I should call this a one-way ANOVA. Okay, there are other types of ANOVA. Is it's a way to test 3 or more means. Okay. Now, the word ANOVA is actually a weird abbreviation for the analysis, and analysis of variance, VA. Okay. Now, the fact of the matter is, it's kind of a weird name. I think ANOVA test. The idea here is you need to check the variance before you can compare means. Okay, so it's kind of it's a weird thing, but we're testing 3 or more means. Now let me show you why we need to compare that variance. Oh, before I do that, let's talk about some requirements. Okay, requirements of the test. Number 1, you need K random samples from each population. So K has got to be at least 3 before you can do an ANOVA test. Okay, 3 or more. Number 2, you're going to have the K samples are independent. Number 3, they are normally distributed. And number 4, we're saying that the populations have the same variance. And here's what we mean by same variance. What we're saying is that the largest standard deviation has to be less than or equal to 2 times the smallest standard deviation. If that's the case, we are saying that those are the same variance. Okay? So let me give you an example.
You said greater than or equal.
No, largest is less than or equal to 2 times the smallest. Okay? Now, in the book, they refer to these as X1, X2, X3. I decided to put city names on them. It's just fake data. But let's go ahead and let's go to Canvas and log into Canvas, go to in-class worksheets. We're going to go down here to worksheet 13.1, correct. Okay. So what I want to do is kind of give you a kind of a visual understanding of what's going on with the ANOVA test. Okay. All right. So let's say that I was collecting some data. Provo, Salt Lake, and Ogden. Okay, so here's my data here. So the mean of Provo is 5, the mean of Salt Lake is 8, the mean of Ogden is 11. Okay. Now let's go through my requirements here. It says I have to have K random samples. I got 3 samples of Provo, Salt Lake, and Ogden. Okay. We're saying that the samples are independent. Those are different populations, so we're saying that these are independent. Now remember, this is fake data; it doesn't represent anything. But we're going to assume that our data are normally distributed. We're just making that assumption in this case. Normally, you should do a QQ plot and check all that out. And then the populations have the same variance. So as we look here, as we look at our standard deviation. Now, by the way, well, it's two times the smallest standard deviation or 4 times the variance, because remember, variance is squared. Okay, so as I look here, my smallest standard deviation is Provo. If I double that, that's 2. The biggest is Ogden. Ogden 1.22 is less than 2. So what we're saying here is my standard deviation is okay. 2 times the smallest is greater than the largest. Or the largest is less than 2 times the smallest. Okay? So we're saying this meets the criteria. Now, I did a box and whisker diagram here so that you can kind of see. So this, the idea here is this is between sample variation. Now this is such weird data that in small data sets that I didn't even have any whiskers on here. But as you see this data here, you can see here that the mean of 5 is probably different than the mean of 8, which is probably different from the mean of 11. These 3 box and whiskers don't overlap at all. Does that make sense? So as we're doing this visually, you can probably say, oh, there's probably going to be a strong likelihood that we're going to say that the mean of this is different than the mean of that, which is different than the mean of that. Now, that brings me up to another point that I want to bring up here with regards to the null hypothesis here, okay? When we talk about the null hypothesis for an ANOVA test, okay? Now, you could say that mu1 equals mu2 equals mu3. Okay? Now, this is one of the very few rules that I'm going to let you break. Or I'm going to say that you could say that all means are equal. Okay? I will let you get away with that, especially if you have like 7 means out there. Okay? Here's why. Your alternative hypothesis, okay? A lot of students like to write that mu1 does not equal mu2, does not equal mu3, but that's not actually what I'm saying here. A better alternative hypothesis would be at least one mean is different. Okay? That's the better alternative hypothesis. Because I'm not, in this case, we're saying that all the means are different, if I write it this way. But it could be that mu1 equals mu2, but that does not equal mu3. Or it could be that mu1 does not equal mu2, which equals mu3. Or it could mean this, or it could mean that mu1 doesn't equal mu3, but does equal mu2. I mean, there's so many different things going on here. That's why, for your alternative hypothesis, we're just saying at least one of the means is different. I don't want to list out every possible combination here. Christopher.
So with the alternative you want, that at least one is different.
Yeah.
And with the
With
null, do you
this,
care?
you could do either way, it's fine.
Okay, either one.
And I'm fine with that. Okay. So, but yeah, this is definitely the preferred alternative hypothesis, because otherwise you're going to have to list out every one, and I don't want to do that. Okay, does that make sense? All right. Now let's go back to our worksheet for just a minute. It always means, yes. But here's why the variance comes into this. Okay. Now you'll notice here for Provo, Salt Lake, and Ogden, I got 5, 8, and 11. Now I purposely constructed this so that with the Logan, St. George, and Orem, I got 5, 8, and 11. I got the exact same 2 means. Okay. But you can see here, I've got much more variation. Okay, now let's check our things here. 2 times the smallest is Orem. If I double that, 4.3 times 2 is 8.6. 5 is less than 8.6. So we're assuming that I have the same variance. It's still okay. Now, as we look at our variance here going on, our box and whisker is very good to see this. You can see that these 3 cities overlap much more than these 3 cities. So it's, from a visual perspective, it's easy to see, hey, I think these 3 means are different. I'm not sure about these. Oops. Do that. There we go. Control Z, undo. I'm not sure about these other 3 cities because they overlap a lot. Okay? So, I don't know. So, the thing that I'm trying to point out here is you cannot simply look at the means and say, oh yeah, they're different. because you've got to include the variance in here. And so that's why we call this the analysis of variance, because we've got to take into account the variance. Because these are clearly different. These are not clear. These might be the same, but is that one the same as that one? I mean, there's a lot of overlap. It's hard to tell. Does that make sense? Okay. So that's kind of where we're going. Now, so that's kind of a visual representation of why we care so much about the variance in this case. All right, so let me introduce to you a bunch more terms. Okay? All right. So let's talk about the SSE. Okay, SSE means sum of squares due to error. Okay? And the SSE equals n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared plus as many samples as you have. Okay? So that's the SSE. The SST equals the sum of squares due to treatment. Okay? So the SST equals n1 times x1 bar minus x bar squared plus n2 times x2 bar minus x bar squared plus etc. as many samples as you have. Okay?
Sum of squares
Due to treatment. SSE is the sum of squares due to error. Okay? Then we're going to have the MSE. The MSE is called the mean square due to error. The MSE is simply the SSE divided by n minus k. Okay. Then we have the MST. Yeah. The MST is the mean square due to treatment. The MST equals the SST divided by k minus 1. And finally, we have the F statistic, which is simply the MST divided by the MSE. So after you do all of those calculations, the F statistic isn't that hard. Now, because the ANOVA test, I just gave it away, the ANOVA test is an F statistic, right? So we've got 2 degrees of freedom. So your degrees of freedom in this case, everything that I put on the board so far is on your formula sheet already. So you don't need to worry about that. But this is the one thing that you will have to memorize. And I'm not going to make you do that stupid table. So forget about that dumb F table. F that table, right? Okay. So your degrees of freedom is k minus 1, n minus k. So that is the one thing, and I'll put a star there, that you will have to memorize. So 90% certain that tomorrow's quiz is going to be on Excel. Okay, so definitely practice this on Excel.
So the degrees of freedom is what we have to memorize.
The degrees of freedom is what you have to memorize, k minus 1, comma, n minus k. Remember, it's 2 sets of degrees of freedom. Okay?
K is a number of.
Okay, so that's a good question. So n equals your total sample size, and k equals your number of samples. Okay, so in our case, going back to what we've got here, In fact, our first example that we're going to do, share the screen, is we're going to compare Provo, Salt Lake, and Ogden. We're going to do the first three, and we're going to see if those are significantly different. Okay? Now, let me give you some steps. Steps to follow. Okay? So number one, find the combined mean, and we're going to call that X bar. That's on all of your data combined. Okay, everything. Okay? Number two, we're going to find sample means. X1 bar, X2 bar, etc., etc. Okay? Number three, we're going to find our sample variances, which is going to be your S1 squared, your S2 squared, etc., for as many means as you have. Step number four, find the SSEs and the SSTs. And step five, find F, which equals your MST divided by your MSE. And then just remember your degrees of freedom that I've got right here. Okay, so that's the one thing you're going to have to remember.
So what's the, we find sample variance?
Sample variances. S1 squared, S2 squared, S3 squared, etc.
So S is not,
S is what?
that's not standard deviation.
S is your standard deviation. S squared is your variance. Yes.
Yes. 2 degrees of freedom then?
Two sets of degrees of freedom. You got your degrees of freedom in your numerator, you got your degrees of freedom in your denominator. Okay? All right, so let me show you an example on how to do this. So basically, here's what I'm going to do. I'm going to share, or I'm going to copy all this data here, is Provo, Salt Lake, Ogden over to here. Okay, so it's the exact same data that you just saw a moment ago. Okay, so I'm going to go through my steps. My step says find my combined X bar. If I take the X bar of my entire data set, I get a value of 8. Try to make these numbers nice. Okay? It's nice when you're using good numbers. Okay? Now, step number 2, I need to find X1 bar. So as I already found that before, the mean of Provo is 5, the mean of Salt Lake is 8, the mean of Ogden is 11. Okay? I'll put them all right here. 5, 8, and 11. Okay? Find your sample variances. Well, I had previously found that before. 1 squared is 1. 1 squared is 1. 1.22 squared is 1.5.
So the easiest way to do that with Excel is just to do standard deviation squared.
Yeah.
So,
Well, I mean, that's the one I remember. Some of you guys are amazing. If stuff you find, you can find the variance command, but why? I already understand. Why do it? I mean, whatever, you can do it. If you want to, I don't care. It won't be the wrong answer. But yeah. Okay, so find the MSE. Let's talk about the MSE, which is really the SSE. So the SSE over here says N1 minus 1. So as I look here, Provo, I have 5 data points. 5 minus 1 is 4. I'm going to multiply that by S1 squared. So 4 times 1 is 4. 4 times 1 is 4. 4 times 1.5 is 6. Okay? Now, in order to find the MSE, I'm going to add those 3 up. 4 and 4 is 8, and 6 is 14. According to my the MSE, I'm dividing that by n minus k. So my n in this case, I have 15 data points, right? So my n is 15. K represents my number of samples. How many samples do I have? 3. 15 minus 3 is 12. So I'm going to take this sum here, 14 divided by 12, 1.16666. Okay? So I've just found my MSE. My MST is going to be found similarly. As I look here, I need to find my SST. My SST is N1. I've got 5 in my first data set times x1 bar minus x1. So x1 bar, 5 minus 8 is -3. -3 squared is 9. 9 times 5 is 45. Okay, we'll do the same thing here. 8 minus 8 is 0. 0 squared is 0. 0 times 5 is still 0. Okay, 11 minus 8 is 3. 3 squared is 9. 9 times 5 is 45. Okay, I'm going to add these three up. 45 and 0 and 45 is 90. Okay, now in order to find my MST, I'm taking the SST, which is 90. I'm going to divide that by k minus 1. What's k again? 3 minus 1 is 2. So 90 divided by 2 is 45. Okay, so I found my MST, I found my MSE. My F statistic is the MST divided by the MSE. So 45 divided by 1.666666 is 38.57. Okay? Now, let's talk about what's going on here. So the idea here is, in fact, I probably should have mentioned this, but I'll mention it again. Okay, so just like the chi-square independence test, the idea here is, as you're looking here, you're trying to see if those are big differences. If those are small differences, x1 bar minus x bar, if those are small, your SST is also going to be small. If those are large differences, your SST is going to be big, right? So your alternative hypothesis, here, at least one of the means is different, is always a right tail test. Okay, so as I'm looking here, here's what's going on. F test looks something like that. Okay, I got a value of 38.57 on my thing here. So in order to find the p-value, it's going to be a right tail test. I need to figure out what that value is, and I'm going to use my degrees of freedom in order to find that. Okay, so does that make sense that this is always a right tail test? Now, one of the things that I did, because there's so, aren't you glad I didn't throw this on your last test? Okay, so I knew there was so many computations. I went through all the computations. I didn't go through the 7 steps. So what I'd like to do, drink water because I'm getting a dry mouth. But what I'd like to do is I'd like to go through the 7 steps. Okay? So let's go through the 7 steps right now. All right. So the first question we have to ask ourselves, is this quantitative, categorical, or regression data? It's quantitative, right? Clearly, these are numbers that represent something quantitative. Okay, I don't know what it represents, but it represents something. Okay, so the next question is, find your null and your alternative hypothesis. So what should be your null and your alternative hypothesis? All means are equal. Your alternative, at least one mean is different. Okay. Third question is, what type of test? Is it a Z, a T, a chi-square, or an F? It's an F because I gave that awfully away, right? What kind of an F test is it? Because there's more than one F test. It's an F ANOVA test. Okay? Analysis of variance. Okay, so I've gone through all the calculations. I've got my F. in this case equals 38.57. I took a picture on the board. Here's what's going on. I drew that just for Russell because I know that he's going to ask for his half-point extra credit on the quiz tomorrow. Okay. So, what's the next step I'm supposed to do? On the p-value. Okay. The p-value is, what do you think? F dot dist, which one? It's always going to be a right-tailed test. Because we do a left tail for the standard deviation test. You can do a left tail on the standard deviation. Okay. What do I put in for x? I put in my F score. I should put F, not X. Comma, degrees of freedom 1 in this case is K minus 1, right? What's my K? 3 minus 1 is 2. My degrees of freedom 2 is N minus K. What's my N? 15 data points minus my 3 samples, 12. Okay. So this works out to be a very small number, right? Just to make sure that we're clear, why does it have an E in there? Scientific notation. So this is really 1, 2, 3, 4, 5, 6. That's what that number is. Okay? And watch what happens when I press enter. Changes it right back to scientific notation. Okay? All right, so now we need to compare to alpha. We'll assume that my alpha is 0.05 since I didn't give it to you. And therefore, reject the null. And our conclusion, at least one mean is different. Okay, now, in the real world, Kendall, if I said at least one of those means is different, what would be your next question to me? Which one is different? That's tomorrow's lecture. Okay? We're going to find out. So if you thought this was a lot of computation, wait till tomorrow. This is a lot of computation. It won't be as, well, I was going to say it won't be as bad as this, but anyway. So as far as the quiz, like I said, pretty certain that it's probably going to be an Excel quiz. So I would definitely ask you guys, recommend to you guys that you practice this on the computer. Your test will most likely be an Excel test, or your quiz tomorrow will most likely be an Excel quiz on this. And then we'll talk about the 2-key test tomorrow. And we'll say, how do you know which mean is different than this? Now, really quickly, we've got a couple minutes left. Here's what I want to do. We've only got about 3 minutes left. But I'm just going to kind of race through the same thing, but we're going to do it with Logan, St. George, and Orem here. Now, this one has a much larger standard deviation and much larger variance, okay? So we're going to do the same thing, 8. We get the same values here. Our variances are very different, though, okay? Find our MSE as of 290 divided by 90 works out to be, in this case, 1.86, okay? We put in our 2, 12 degrees of freedom. I get a value of 0.19. What does 0.19 mean? Do not reject. There is not enough evidence. Now let me go back here. Let's just look at these again here, okay? Remember the first time, 5, 8, and 11, we said those are different and they look different. Now we've got 5, 8, and 11, exact same 2 values. What we're saying here in this case, just to make sure that we're super clear, we can't tell the difference between the 5 and the 11. 11 is more than twice as big as 5, right? Wouldn't you think that would be different? I don't know. We got so much variation going on. We can't tell if 5 is different from 11. Okay? There's just too much overlap going on here. We cannot make a call as to whether those are significant. Does that make sense? And so you can kind of see the role, and that's what we call this an analysis of variance test. You can see that the role that variance plays in whether you can make a conclusion either different or not. Okay? All right. Quiz tomorrow, ANOVA test 13.1. See you all tomorrow.
I have a question real quick.
Okay?
So my